Good morning, everyone, and welcome to the second day of the workshop. This morning we have a few talks on network inference and statistical methods based on network structures. And our first speaker this morning is Peter Bühlmann from ETH Zurich. Peter is very well known for some of his seminal work on the inference of high-dimensional graphs. And today he's going to talk about sparse graphs and causal inference, which I think will be very interesting to hear about. So, Peter, take it away.
Thank you. I would also like to thank the organizers for having invited me here. I enjoy being here. I always enjoy being here at the Newton. So this is joint work with Marloes Matthaus and Markus Kalisch. They're both also at the seminar for statistics at ETH Zurich. This has nothing to do with the Graduate School of Accounting. It doesn't exist at ETH Zurich. So in the book of abstracts, as Fred just mentioned, there's a slight mistake here. So we're just in the math department. So the talk has nothing to do with communication or social networks, but it involves graphs. And from that point of view, it is something on networks, but it's maybe a bit an outlier talk. But nevertheless, I tried to convince you that this is also kind of interesting research. As Rob mentioned already a bit, I have been working a lot on high-dimensional problems. This is again high-dimensional statistics, but from a quite different angle. But maybe as an introductory slide, I should say that I really think quite a lot is nowadays known about high-dimensional regression, classification. And suppose in a very simple linear model where you have a univariate response, you have very many covariables or covariates. So here is a linear model. Everything is standard except that the number of variables, p, the number of covariates p may be much, much larger than sample size n. For example, p can be 1,000,000 and n can be in the dozens or hundreds. And obviously we need to regularize if we want to do estimation in such models. And I really think substantial progress has been achieved over the last, say, 10, 15 years on high-dimensional problems. Notably, the lasso, L1 penalization became very important. Then version of the lasso. I mean, you see essentially every 2 weeks another version of this kind of technique. People use Bayesian methods and so on and so forth. And I really think we understand quite a bit about high-dimensional regression classification nowadays, but I'd like to convince you today that in some applications, in some examples, in some important examples, high-dimensional regression doesn't do the job. And here is one of these examples. This is an ROC curve, and this is really about selection. So it's selection of variables, so to speak. Like in a regression model, you want to know which of the x variables are important for your response y. And here on the x-axis, you have the false positive selections. Here you have the true positive selections. And there's this fine dotted line here, which is maybe hard to read from the back. But the fine dotted line here is random guessing. And then you see two sophisticated regression techniques, the red and the blue dashed line. This is lasso and elastic net. High-dimensional, sophisticated techniques. And what we find here is you're not essentially doing better in random guessing. So sophisticated regression methods don't do a better job than random guessing. And here's another technique, which I will explain in the talk, which does substantially better. Okay, so the talk is really beyond penalized high-dimensional regression classification. We need something else. And I would also like to say what the example is all about. And then I will come back to the example towards the end of the talk again. So these were effects of single gene knockdowns in yeast. And so measurements were taken from gene expressions, a bit more than 5,000 gene expressions. These are the variables, the p. Then there are 231 intervention experiments, knockdown experiments where a gene has been knocked down, and then you see what's going to happen on all other genes. So you can actually look at the interaction effects between the genes, and in total there were a bit more than 1 million intervention or interaction effects. And the issue is the truth, in the sense of that we know what's happening if we knock down a gene is known in good approximation. What happens is you knock down a gene and some other genes show a huge effect. And if they show a huge effect, we say, okay, this is a true relevant effect, what we see, and maybe there are some medium effects, and then we don't make any claims on that, but at least for the strong, huge effect, we know the truth in good approximation. Now the goal in this example is, can we predict actually these intervention effects, these intervention experiments, without doing the experiment? Okay, so again, people knock down in yeast a gene, this has an effect, and I would like to predict before actually doing the experiment what would happen if I knock down this gene. Okay, so this is well known in the causal literature or in the intervention literature, is the prediction of the true, at least large intervention effect based on observational data only, which means based on non-intervention experiments only. Okay, and what happened here in this picture is we had 63 non-interventional measurements, kind of steady state measurements, and then we tried to predict these 231 gene knockdowns. And this is the result. We're having quite a bit better capacity for prediction of the true large intervention effects. And I will explain in the talk what we're doing here. Okay, so why is this interesting? And this has been taken from an editorial in Nature Methods recently, and I'm just kind of reading again what is written there. It says causal inference, which is really the same as inferring intervention effects from purely observed data, could have a practical value in the prioritization in design of perturbation experiments. And this is the main motivation of our work. I'm closely collaborating with biologists, and if you can give them a clue or a better clue where they should do their experiments, this would be a tremendous leap forward in design of experiments. Okay, that's kind of the main motivation why we want to do this. Okay, so why are we doing substantially better than any kind of fancy, sophisticated, regularized regression? And the reason is really the problem is of intervention type. It's not a regression type problem. And I just want to make sure that you see that this occurs in many application areas. So many scientific problems are of intervention type effect. So for example, health policy making, this is a well-known area and many people use this causal intervention type technique. The question is, what would happen when you would implement a healthcare program X? Okay. Or in genomics, this is what I explained already, what would happen when changing some of the genes? Or in economics, it's again policy making, what would happen if you would implement this policy? And it's maybe worth noting or emphasizing James Heckman. He got the Nobel Prize in economics in 2000 mainly for his work on policy making in economics on intervention analysis. Okay, so when I say intervention, this is the same as causality. So causality, it's a very ambitious word, and mathematically, and I will define it, it's really what we see or what we understand as an intervention effect. If I make an intervention, what would happen? This is what people call causality. Okay, let's be a bit more specific now what we're doing here. So we have in mind a univariate response variable, say an effect on another gene, and we have many other explanatory variables, x, p of them, p can be large. And the question is, again, this is rephrasing the question, what is the effect if I set the jth component of x here to a certain value little x? I make an intervention at the jth variable and set the jth variable to a value, a deterministic value little x. And this can be formalized with this do operator, which is due to Pearl. We just write, I make a do xj equals little x. Okay? And again, the question itself is a question of intervention type, not association. This is really in contrast to regression. What is regression doing? So in the Gaussian world, we know the variables have to follow a linear regression. So let's look at this linear regression here. You have a response y, I have covariates x. I scale them just for convenience. And then we all know that importance of a variable could be measured in terms of the regression coefficient. For example, beta j absolute value, the absolute value of the regression coefficient is a measure of how important is the jth variable on explaining y. Okay. And it measures, this is trivial, this is textbook, right? I mean, it measures the change of y as a function of xj. Now it comes the important part, when keeping all other variables fixed. Okay? And this is not realistic for this gene problem or for many other problems. If I change a gene, if I change a variable, maybe many other variables will change. I cannot keep them fixed. And so I need to do something else than regression because I cannot keep the others fixed. Okay, so this is the outline of the talk. I will use intervention calculus. This is essentially due to Pearl in his book, but many other people in causality like Phil David here from Cambridge worked on that. This is all the same. So I will use this, and as kind of the novel contribution, we really put it into the high-dimensional sparse context and kind of do the estimation part on that as well. Okay, so I think most of you are not familiar with the intervention calculus, and I show you what it is so that you kind of understand really the difference between, say, regression and this intervention. So intervention is really, in some sort, a dynamic notion of importance. And I'll explain a bit again here. So dynamic in the sense that if I set a variable xj to some value x, some other variables may change as well. And what I would like to do, I would like to quantify the total effect, including all these other changed variables. Okay, this is the goal which I want to achieve. And I think some graphs and influence diagrams will be quite useful. So here is my response y. Here is my x2 where I do an intervention. I have two other variables, x1 and x3. In this example, what I would like to do, I would like to quantify the effect of x2 on y. There is this direct effect, but there are two indirect effects here, y x1 and y x3. And I would like to quantify the total effect. Okay? So if I set this to some value, x1 and x3 will change, and all these have an effect on y. This is another example. There are no direct effects. There are only indirect effects, right? If I make an intervention at x2, x1, and x3 potentially change, and then y will change as well, but only indirectly. Okay, so to set up the framework for simplicity in this talk, I will just consider DAGs, directed acyclic graphs, where everything is measured. You can move on to ancestral graphs. I will skip that topic. So suppose somebody gives you a probability distribution which is Markov with respect to a directed acyclic graph, then it's well known, then you can factorize the joint distribution according to this formula. You just need to condition on the parents in the graph. This is a very well-known formula. So the joint distribution is P of y given the parental nodes and then the product of all xj given the parents of xj. Okay, so this is the basic formula. This is well known. There's nothing new. And now for the intervention calculus, we use a truncated version of this formula, which will do the job.
Sorry, question. What's the difference between the interaction effect in a normal linear regression when you basically try to understand interaction between x1 and x2?
Say it again.
When in a linear regression, you have x1, x2, xp plus all the interaction effects. So you have x1 multiplied by x2 plus blah, blah. So what's the difference between intervention calculus and interaction effects in normal linear regression?
Okay, maybe I'll try to. So the calculus comes now next. So, but maybe also I will only focus on the Gaussian world today. Although your example could also be covered, but in the Gaussian, the linear doesn't involve interaction terms. But that's not the main business here, whether it has interaction or not. I'll try to say now what the intervention is doing, and then you may see, and otherwise you'll ask again. Okay, so here is just the well-known factorization when you have a probability distribution on a graph, which is Markov on the DAG. Okay, now let's do the intervention. And I think the example is more instructive here. So let's take this example. Okay, let's do the factorization as on the previous slide. So the joint distribution factorizes P of y given the parents are x1, x3, x1, the parent is only x2, x3, the parent is only x2 times px2. And red means I do an intervention at x2. Okay? So now the intervention distribution, now I want to compute or calculate something. What is the distribution of y, x1 and x3 if I make an intervention at the second variable? And this is now just a formula, and then I explain a bit why the formula actually holds. So I just take this factorization. I write here a do x2 equals little x. I take the factorization, and whenever there is no x2 involved, that factor just remains. Then there is this other factor here, and this is just a standard conditional distribution. P x1 given x2 equals little x. Then here also you just substitute a little x here, and you do an intervention for sure, so px2 just will drop away, and it's just a 1. Okay, so far it's just a formula, but it's a quite automatic principle how you can come from the general factorization to the intervention distribution if I make an intervention at x2. And then I can also do things like, what is the distribution of y when I do the intervention at x2? I just integrate out over the other two variables, x1 and x3. So once I have this, it's just standard probability calculus. Now you may wonder a bit, I mean, what does it mean if I just do this automatic truncated factorization? And
it's a lot harder if you condition on x3, for instance. Look at your example in the previous slide. Suppose you said do x3 equal to x.
Okay, if I do x3, then it's just p1 x1 x3 equals little x. Then
there's backward influences to x2 and so on. So it's not so easy to write down a conditional probability like that.
Say it again.
It has backward influences, right, to x2 and so on. So
no, that doesn't occur anymore. So
that's not your meaning of an intervention?
Excuse me?
I mean, an intervention seems like a conditional, evaluating a conditional probability.
Almost.
Condition on x3 equals x, so it's not the same thing.
It's not the same thing.
I see.
No, it's not the same thing. I mean, you really, okay. When you, if you look at this intervention distribution, what it involves, it involves indeed standard conditional distributions, but it involves also the graph structure. Okay. So once
just need to understand your definition. So.
Yeah, well, unfortunately, I do not really give you the full definition. So
if you did an intervention on x3, then that p of x3 given x2 would just be a 1, right?
Yeah, exactly. So that crosses away because you do an intervention there, so that's exactly. You can also do it in the graph, I mean, just delete edges and so on, but I think this is maybe a more algebraic way to explain what's going on. Okay, so unfortunately, I'm not really giving you the definition because it's a bit time constrained, but this truncated factorization, this formula, is a mathematical consequence of assumptions we're making. And the assumptions are quite standard in graphical modeling. The first assumption is, well, it's the Markov condition which you require, and you think that you have a true underlying DAG, which is which explains the causal relationship. So you have, somebody gives you the true DAG, this is the true underlying causal relationship, you put the Markov property on that DAG, and then the truncated factorization is a consequence of it. Okay. So, this again, what I said already, the intervention distribution can be calculated from, let's do this, from standard conditional distributions and the DAG and the graph. Once you have it, you're done. Okay, and this is something, standard conditional distributions, this is estimable from data, right? If you have observational data, I can estimate the standard conditional distributions, and hopefully I get also a reasonable estimate of the true underlying influence diagram, but that will be the hard part. Okay, so this is so far still only probability, no statistics involved. Now let's talk about, well, the average effect of the intervention of x2 on y. I can just do anything like with standard probability. This is just the integral of the intervention distribution, and the intervention effect is typically defined as the derivative. Okay, I do the derivative of this expected value of y when doing the intervention in x2, and it turns out in the Gaussian case, as with conditional expectations, but it's not the same, but as with conditional expectations, this is linear in x, so the derivative is a single coefficient, a single number. So in the Gaussian case, an intervention effect is a single number, a single coefficient. Okay, so what is this intervention effect? Well, this is what people call the causal effect. And, well, this is this big assumption here when having no unmeasured confounders. So it kind of means if you measure everything in your system, then what is this causal effect? This causal effect is actually the effect which you would see from a fully randomized trial. Okay? And this is, of course, the classical view. You should, to find out causality, you have to make a big trial, you should do randomize, but the point is often you cannot do a randomized trial or it's too expensive to do. And that's the thing which we want to achieve. We want to find the effect like from a fully randomized trial without doing the randomized trial, just from pure observational data. Okay, so here's an important characterization how you can get to this goal. In the Gaussian case, this is a recap again. The intervention effect is just a single coefficient, and there is a beautiful, very simple characterization of this single number. And it goes as follows. Here's again an example. So here's my y, here's my intervention I'm doing at x2, and I can find the intervention effect of x2, for example, through this characterization. If y is not in the parental set of x2, where I do the intervention effect can be found by regression. I regress y on the variable where I do the intervention, this is here the second variable, and on all other variables which are the parents of the variable where I do the intervention. It's a bit counterintuitive. So I run the regression of y on x2 and the parents on x2, this is x4 and x3, and then the coefficient in that regression, that is the intervention effect. This is Pearl's famous backdoor criterion, and turns out this is a very simple characterization of the intervention effect. So all what I have to do to find it is I have to run regression, that's easy, and I have to know the parental sets, and that's difficult. Okay. So intervention is really very different than association or regression. Here's again this example. This can also be written down as what people call a structural equation model. Y, the response, is a function of x1 and x3 plus error. x2 is just some error term, so to speak. x1 depends on x2, x3 depends on x2. So this is the structural equation model. So let's compute this intervention effect of the second variable, which quantifies the total effect of x2 on y. If you go through this calculus, you will find the intervention effect is 1.6. Whereas the intervention effect of x1 and x3, vice versa, is only 1. So x2 has the largest intervention effect in this example. Now, if you compute regression, you probably know how to read this graph. You all would read this graph probably that y is conditionally independent of x2 given x1 and x3, and that's true. And that means the regression effect of x2 is 0 because it's conditional independence. Okay? So if you would run regression here, you would say x2 has no effect, no association effect, and that's true. And x1 and x3, they have an effect of equal to 1. So it's just really the opposite what you find here. So x2 has the largest intervention effect, but the smallest regression effect.
But if you measure the interaction effect, you will find that x1, x2 are related, and x2, x3 are related.
Yeah, that's true. Yeah. So with your interaction example, that's true. However, again, if I just assume the system is purely Gaussian, the interactions do not occur. But I mean, the issue is, let's just say x1 times x2 is another node in my graph, and I can deal with this. So conceptually, it's no problem. Okay, so this is really just the framework, what we want to do. And now comes how do we infer this intervention effect from data. And the main problem is the graph. The other one is just regression. And it's well known in graphical modeling, you cannot do it. I mean, suppose somebody gives you data, somebody gives you the full probability distribution, like the infinite amount of data, you can only infer an equivalence class of graphs. And the easiest example is you have two Gaussians. If somebody gives you the distribution of two Gaussians, you can never say whether it goes this direction or that. It's just, you can only infer the equivalence class. And because of that, if you can only infer the equivalence class, you cannot infer the causal effect because it hinges really on the underlying DAG. And I think in a way that's one of the main reasons why many people have given up on this. They said, well, it's impossible, and I agree. I mean, there's nothing you can do on inferring really the causal effect if somebody doesn't give you the influence diagram. So causal inference literature typically goes like, you have the influence diagram, and then you do the causal effects. But we don't have the influence diagram. However, there's something you can do with this, and what you can do is you can get lower bounds of the causal effect, and I try to explain this in this talk. So you don't have to give up completely. You can still do something. Okay, and here is a conceptual procedure. It's really a hard identifiability problem what we're dealing here with. And I try to explain this a bit. And then we kind of can see maybe how we can infer the lower bounds. So the conceptual procedure is as follows. Suppose you have an infinite amount of data. Suppose you have the probability distribution P. Then what you can infer is the equivalence class of the true underlying DAG, or the true underlying equivalence class. This is something you can do. It's a hard problem, but you can do it. Then conceptually, not practically, but conceptually, you can just enumerate, find all members, all graphs, all DAGs in this equivalence class. Okay? So suppose these are my graphs G1, G2, Gm. And then for every of these graphs, for every of these DAG members, I compute this intervention effect as explained. So if I have a DAG, if I have the distribution, I can compute the intervention effect. And I can just store this whole thing in a matrix cap theta. So this is the theta rj, this is the intervention effect from a variable j, and r is the index of the graph in my equivalence class. So it's kind of a huge matrix theta. But this is the parameter, so to speak, which is identifiable from observational data. If somebody gives you the P, the distribution, you can identify this parameter cap theta, conceptually. Okay, that's not that great. You really want to have a single number. And now comes a trivial construction, which is quite useful. So we have this theta. And then you can say, okay, let's just fix a j, a certain variable where you do an intervention. And then you say, okay, let's just take all these graphs in the equivalence class, this theta rj, the corresponding intervention effect, take absolute value and take the min of those, call it alpha j. And then trivially, the true value, it is one of your true DAG members, is lower bounded by this alpha j, because the true one is one of these theta rj, and if you take the min here, you know the true underlying causal effect is at least as big as alpha j. This is trivial, but it's quite useful. Okay, so we can infer from P a lower bound on causal effects. Now there's this big issue here. I mean, find all DAG members in the true equivalence class, and this is a horrendous computational task. And I just want to say here, there exists a computationally tractable algorithm. We suggested in an algorithm we can prove that this algorithm actually finds what we want. So obviously searching all DAG members in the equivalence class is an impossible task if your graph is large. If you have many nodes, the equivalence class is way too large and you cannot find or easily find all the DAGs. It's just a very hard problem computationally. Typically you can do it in some sort of sparser graphs when you have 15 nodes or 20 nodes, and that's it. But we're dealing here with 5,000 nodes. So the trick is, instead of really trying to find all DAGs in an equivalence class, you can compute this theta without actually finding the DAGs. And that's kind of the clever little construction here. And the reason why it flies is really this algorithm, it works only on local aspects of the graph, and local is enough. And it really has to do with this characterization here. You only need the parental set, you don't need the whole graph. So that makes the argument fly. Okay, so you can compute this cap theta with a computationally tractable algorithm. It only works on local aspects of the graph, and we can actually prove that this algorithm finds the theta. This is not statistics yet. This is still only how to compute the thing. Now comes the statistics. How do we do the estimation from finite samples? And obviously the difficult part is, how do we estimate the equivalence class of DAGs? That's the hard part. And there's quite a beautiful characterization of the equivalence class, and you can also write it down in a little network or a graph, and it has different edges. So for example, from 1 to 10 there is a directed edge. And this means that every member in the equivalence class must have an edge from 1 to 10 in that direction. Sometimes you have bidirected edges, and this means that some members in the equivalence class must have an edge in this direction, and some must have the edge in the other direction. And if you have no edge, it means all members in the equivalence class have no edge. Okay. So this is quite a lot of structural information. And so the thing is, you can estimate this object from observational data only. In principle, how you can do this is from a huge list of conditional independence statements. Suppose you would know whether xj and xk are conditionally independent or dependent given some other variables x, s, and s is a set of indices for other variables. If you have this thing for all subsets S, then you can determine it. Now this is again a killer. Computationally, you cannot go through all the subsets. And this is an NP-hard problem. And what are people typically doing when they have an NP-hard problem? You look for some conditions under which the problem is computationally feasible and not NP-hard anymore, or not, it becomes computationally feasible. So we make some sort of assumption. And the assumption which we make and which people typically make in graphical modeling is the so-called faithfulness assumption, which I will explain a bit. And the faithfulness assumption as an implication will mean that you don't have to go through all subsets, but only through some subsets. And that's why the algorithm becomes feasible. Okay, what is the faithfulness assumption? It's in a way something which you anyway implicitly think about a graph and probability distributions. So a distribution P is called faithful to a graph or a DAG if all conditional independencies can be read off from the DAG. Okay? You think, well, that's usually what we think of, but it's not quite true. So what we typically think of or do is we have the Markov assumption on the graph, and the Markov assumption says we can infer some conditional independence statements from the Markov assumption, but not necessarily all of them. So faithfulness goes beyond Markov. You require that you can read off all conditional independencies from the graph, and not just some. Okay, so here's an example of what does it mean in very toy problem. 3 variables, it's a DAG. Here's the structural equation model. So x1 is a noise variable, x2 is a function of x1, x3 is a function of x2 and x1, and the noise terms are IID standard Gaussian. So here is the graph of this structural equation model, and if you look at this graph, you think everything is dependent of each other, right? It's fully connected and so on. But the issue is I can enforce marginal independence of, say, x1 and x3 for a particular parameter constellation. If you choose the parameters alpha, beta, gamma such that beta plus alpha, gamma is 0, for example, alpha, beta is 1 and gamma is minus 1, then let's just compute the sigma for this little problem. Then sigma is this. So then you see from the covariance matrix, x1 and x3 are independent because the correlation is 0, it's Gaussian. Okay, so you have marginal independence between x1 and x3 for this parameter constellation, but you have conditional independence. You have marginal independence, but you have conditional dependence. The sigma inverse has no zeros. So conditional independence or dependence is characterized by sigma inverse here. Okay? So again, you can enforce marginal dependence by a particular parameter constellation, and what faithfulness assumption kind of requires is that there is no strange cancellation of these regression parameter effects. That's what faithfulness assumption really requires. Okay? You forbid this kind of thing. Okay, so what can you do to do this problem, this graph estimation problem? We use mainly the PC algorithm. This is called after the inventors Peter Spertus and Clark Glamer. It has nothing to do with a PC or a laptop. It's just Peter Spertus and Clark Glamer. They proposed this algorithm in their first edition of their book in '91. There's a crucial assumption here, which is this faithfulness assumption. P is faithfulness. Is a less crucial assumption which makes things convenient. We assume the Gaussian world. Okay, the strategy of the algorithm is you estimate the skeleton first, just the graph without the edge directions, and then in a second stage you put on edge directions. Okay, and so maybe I can just explain a bit roughly how this goes. Well, this is just large enough. So you have a graph, and let's just do the skeleton first. In the beginning, everything is connected with everything. That's about it. You start with the fully connected undirected graph, and then you ask the question, should that edge here be present or not? And the first thing you're doing is you do just marginal, you check for marginal dependence or independence. In the Gaussian world, you just look at the correlation between these two nodes. And suppose the correlation or the empirical correlation is small enough, you delete that guy, and maybe this one is deleted, and maybe that one. Just by looking at marginal correlation, you can delete some edges. Okay? And statistically, this is easy. You can do a test. It's exact in the Gaussian world. You do Fisher's Z transform, and you're there. Okay, this is this formula. Remove. Okay, then next is you still question, for example, whether this edge should remain or not, and you move up to partial correlation of order 1. And now the trick is, due to this faithfulness assumption, I only need to do partial correlation of order 1 given the conditioning variables are just in the neighboring or in the adjacency set of this and this variable. So for example, well, this is not a good example, let's delete that as well. This cannot be a conditioning variable anymore because it's not in the neighborhood of this and this variable. Okay? Then you, again, if partial correlation is small, you delete it. If it's not that small, you leave it. Then you move up to partial correlation of order 2, and so on. And the trick is always, due to the faithfulness assumption, you only have to look at conditioning variables in the current adjacency set where you are. And you do that until no removal of edges is possible anymore. And then in the second stage, you can add directions and we'll leave this apart. Okay. So there's one tuning parameter involved here. It's kind of your testing, your multiple testing label, call it an alpha. And the other thing is, what happens here? If the true underlying graph is sparse, if you have very, very many nodes, but the true underlying graph is sparse, this works because the conditioning sets, I mean, they're only very kind of small adjacency sets, and that means you only look at partial correlation of low order. And this is statistically possible even in the high dimensional context. You get away with low order partial correlations because of sparsity of the graph, because the adjacency sets will not be big. This is an assumption, this is a sparsity assumption. You can do it in a very high dimensional context. And also computationally, it becomes much faster if the graph is sparse. So here's actually computation. It's crudely bounded to be polynomial in P. It's still quite a bit of work, and obviously the sparser the graph, the faster the algorithm. I should just say we can easily deal with graphs in, say, dimension P equals 10,000, and it takes about 1 to 2 hours CPU to do this. It's not immediate, but nevertheless, you know, a graph with 10,000 nodes, it's quite an object. So here's a theorem on asymptotics that this is actually all consistent. The assumptions are multivariate Gaussian. This is for convenience. This is a crucial assumption, the faithfulness assumption of the true underlying DAG. Then the dimensionality can be very high. This is a standard kind of trick and assumption in high dimensional statistics. Dimensionality can grow as a function of sample size in an arbitrary polynomial order. And then the next thing is you need to have sparsity, so the maximal degree of your graph should be of lower order than sample size. Otherwise, you cannot do it. And then there's also this issue on signal-to-noise ratio. The non-zero partial correlations have to be sufficiently large, larger than 1 over the square root n range. And then you can prove that you can consistently estimate the true underlying skeleton, the true underlying equivalence class, and also this true set cap theta with all the potential intervention effects, and from this we get a consistent estimate of the lower bounds of the causal effects. Okay, that sounds all great, an algorithm which is feasible, a theorem which says it works, but there are 2 criticisms at least. The first one is the faithfulness assumption. You have no idea in practice whether it holds or not. And the other one is the well-known signal-to-noise ratio problem. There may be many small partial correlations which are not really sticking out, and we don't quite know what's happening then. Yep.
What about just whether or not this lower bound is anything better than something trivial?
Okay. From a theory point of view, we don't have an answer. From a practical point of view, we just see the lower bound, for example, in simulation examples, kind of obvious. I will come to that if I have a bit time. The sparser the graph, the tighter or the better the bound, the lower bound. But we don't have a theoretical statement for this. Okay, maybe I'll skip that, but I just say one word. People were very eager to have some convex relaxation on these kind of discrete structure estimation problems. Like the lasso for variable selection is tremendously popular. And this is also variable selection is a discrete estimation structure problem, but here it's much, much harder because the underlying parameter space is non-convex. And I'm a bit skeptical so far whether people can really come up with a convex relaxation of estimating the true underlying equivalence class. I don't know the answer, I think nobody knows it. Okay, so this is a bit your point, the role of sparsity in this business. I mean, typically sparsity has been used in high-dimensional statistics so that estimation works. Because if you have a sparse structure, then we can regularize, and then even if you have a high-dimensional problem, we can estimate the object of interest. Here, sparsity is also an identifiability issue. And let's just explain this example again. Let's take two Gaussians. I told you already, if somebody gives you the probability distribution, you can never infer whether x causes y or y causes x, right? And the reason is, this is a fully connected graph. You have two nodes, it's fully connected, you're lost. You can play the same game with three nodes. If you have the fully connected graph, you're lost. You cannot just say anything. However, if you have many nodes, and this is kind of like the benefit of having a lot of variables, and if the true underlying sparse graph is sparse, then there's a chance that you get better identifiability. It kind of sounds plausible, and I'm skipping the argument, but let's look at this picture again. I mean, this is actually a true model, a true underlying Gaussian model, and here you can identify some effect. For example, this model is sparse, it's not the fully connected graph, and for example, this edge and this one and this is unique. You can identify here the causality. Not always, but in some parts of this more sparse graph it's possible. So remember, the sparser the graph, the better the identifiability properties. And this is really something in addition to the classical sparsity from statistics. How well can we do? Well, I think my time is running out. Okay, this is a very hard problem. It's a very high-dimensional graph. I don't believe yet that we can actually infer the real topology, say, in this yeast genomics example. I think this is very hard or even impossible, at least on the basis of so few observations. Nevertheless, the success here is really that it really helps you to get better predictions of intervention effects. And what's happening in this genomics example with yeast is you cannot predict the medium intervention effects. It's too hard. But you have a chance to predict the real strong high effects. And this is what you see in this ROC curve. This is actually a zoom in. If I would show you the full ROC curve, eventually the black line is also not much better in random guessing. But at the beginning, in the lower left corner, you're doing a substantially better job, and this is actually the corner biologists are interested in. I mean, they're running maybe 100 experiments, not more. And that's where they want to prioritize what is important and what not. I think there are no real comparisons here. I mean, maybe some people in computer science run other algorithms. We have here a methodology which is backed up by solid mathematical arguments, at least are asymptotically. It's computationally feasible. We can run it for large P. I believe very much there's ample room for improvements, but nevertheless, we saw some real success on this biological example. By the way, if you do, for example, bootstrapping on this example, it doesn't fall apart. It's quite interesting. I mean, there are strong signals which are just there. This is work in progress. I think maybe I should point out the active learning area. What we should combine is really observational and intervention data together. Biology is full of that. They have intervention experiments, they have observational data. You could just combine it together, and there's an active learning issue here. What is the next best intervention experiment which we should do in order to gain most information? Okay. Conclusions. In the Gaussian case, you can infer bounds. You cannot infer the causal effect, but you can infer lower bounds on the causal effect. Even in the high-dimensional sparse context, this is computationally feasible and statistically consistent. At least for us, the computations are non-trivial. The efficient computations are non-trivial, and so that others can use it. We have an R package for it. And I think I should stop and say thank you.
You have introduced this faithfulness concept in order not to consider all subsets. But in order to check this condition, you have to consider all possible, say, conditional distributions, say, for all subsets of nodes. So somehow, is there any kind of useful criteria, or at least not criteria, but sufficient condition not to check all the possible say, subsets of variable? So how would you really say that the distribution is faithful or not?
So the question is a bit, I mean, if I understood you correctly, why do we get away by not looking at all subsets? Is that
You assume something that actually implies looking at all the subsets.
Yeah. So the reason is really this faithfulness assumption. With this faithfulness assumption, as a consequence of this, you don't have to look at all the subsets. And
Yes, consequence, yes, but how do you check this assumption?
oh, it's impossible. I agree. I mean, somebody gives me some data, it's impossible. Even if you give me a probability distribution, that's a good point. I think even then I could not easily check whether it's faithful or not.
Isn't there, you could say something to like the set of coefficients or something has measure 0.
Yeah, that's an I mean, we actually write this in
Some
papers.
weird algebraic variety that's bad.
And other people write it this way. I agree. I mean, that's the way typically write about this, and it's a useful concept. So here, why is it failing? Because the coefficient have a very special constellation, right? And now, if you think about more in some sort of, say, Bayesian way, where your coefficient have been sampled according to, say, a continuous distribution with respect to Lebesgue, this has measure 0. So that's the kind of argument. But the real, I mean, I agree, you can easily get out of this, but it's a real issue. The question is, what about near faithfulness? So if you have estimation where you only get accuracy to the 1/√n range, I think nobody has a real solid answer to it. It's an open problem. I agree, it's a real issue. And the checkability of the condition is a bit like, let's look at what people are doing in the sparsity statistics. They have incoherence conditions. I mean, some of them are checkable, but the sparse or restricted eigenvalues, they're not checkable. So, and I think in statistics at least, that's fine to a certain extent. Of course, you would like to check it, but the models are wrong anyway. So, I mean, you try to get an idea how broad is the range of problems where this is still giving reasonable answers. But I agree, we cannot check it. So, yeah.
How's the performance of your approach compared to approaches that are somewhat simpler but still going after an intervention effect, like a marginal structural model, where you're looking at the conditional distribution of your predictor variable based upon all other predictor variables?
But with the marginal structural model, you need to have the structure, right?
No, you just, if you have your x2 as your causal, as your variable of interest, then you look at whether x2 is predicted by x1 and x3.
Yeah, okay.
And then you just weight that in a regression of x2 against y. So it's going after the same thing, but it's...
Yeah, no, I think that's quite similar. I wouldn't bet on it that it is 100% the same, but again, so if you extrapolate that to a larger graph, you need to run a lot of tests or regressions to find out whether x2 plays a role and so on, right?
But all you need is a model of x2 on all other variables, and that can be something very, very simple, like a lasso, because they're just looking for associations. So you use an association test to look at what's going on with x2, and then you can go on and look for an intervention effect of x2 on y.
And how do you do the intervention effect? I mean, then you still need the graph, right? Or
No.
okay, maybe we should discuss this, but
I think let's move on to the next talk. Peter will be around, so if people have other questions, you can find him at the break. Thank you.